I think your next point is maybe closer to home for machine learning and computer vision, and it's a big one that has a lot of people talking,
Yeah,
and it involves transformers, not the robots, of course,
not the
but the
robots.
transformer networks that we all know and love. What are you seeing there?
Yeah, I mean, this has definitely been a highlight for 2021 computer vision. We have seen Transformers finally coming into computer vision. Transformers is actually not in natural language processing (NLP). Researchers there have been working with Transformers for a few years now, but they have finally made it to into computer vision. Um, and it has been an exciting times because we now sort of are seeing this line of work where we are slowly replacing CNNs with transformers and for various recognition tasks.
Hmm.
Um, and in particular, we've also seen what is exciting about transformers and computer vision is their impact when it comes to working with extremely large scale data. So it's still quite unknown to us whether transformers work well in the low data regime. This is something that is, the answer is not out yet, but we definitely know that for large data, we're talking hundreds of millions of images and more, transformers are quite impactful.
And is the idea that transformers can create more robust representations based on lots of data than convolutional networks?
Yeah, so I think that again, this is we don't quite know, and like theory behind these
Yeah.
things is kind of always unclear. But the main sort of highlight is that so CNNs, which is the predominant sort of tools that we used before to represent our visual inputs, had inductive biases, and this comes from exactly the structure of convolutions and the image grid. Now, transformers take a completely different approach. They actually treat images like a sequence of tokens. So this can be patches of images, so small neighborhoods of the image,
Hmm.
um, and they and the only inductive bias that comes into transformers is through this serialization, as you would say, of the image, and the pose embedding that comes in when we are processing these inputs. But other than that, everything, all operations are sort of global with attentions being cast into these representations. So there is no other inductive biases in these networks whatsoever. So that means that they have the potential to be a lot more powerful because you're constraining them less. But in order to achieve that, you need more data. So it is a much more it is much closer to actually having a true function approximators, like what we say, like MLPs are great function approximators. But with CNNs, that was a little bit taken away because of that particular structure, and now transformers are bringing this back to life, which is an exciting and has proven also to work in for images.
And how would you characterize where we are? Are we in the, just kind of demonstrating that it's possible to make it work stage, or have transformers in computer vision demonstrated, state of the art results, or, either better results on, known tasks or tasks that we were doing pretty well on, or, allowing us to perform tasks that we weren't able to perform well with CNNs.
Hmm. I love that question. And I hope that my answer is not going to anger people. But you know, I it's a great question, and I hope and I wish we asked it actually more often.
Mm,
So you know, before I answer that, I'm just going to go a little bit to the NLP world and say why I think transformers have had a tremendous success.
mhm,
I think it's partly due to two reasons. First is that you know in NLP, you can actually get a lot of data, and that's what works like BERT have shown, where you kind of crawl the web and you get all sources of text data.
mhm.
And there's a lot of that out there.
Yeah.
And now you show how, and it can be anything, any. any text whatsoever, whatever content, and you feed that to the beast called transformers, and it builds a representation. So that's fantastic and a first great milestone. And the second one is that they have all these fantastic tasks, diverse tasks like question answering, text generation, or text fill. Like their tasks are endless, and they are very different from each other. And they have shown that even in those very diverse tasks, having a global representation coming from, you know, learning through self-supervised learning with a lot of data is helps all these tasks significantly. Now in vision, in computer vision, things are not quite like
The
that.
folks
First
that
of all,
follow computer vision probably have a sense for where this is going.
correct. So, we are kind of in a weird, awkward phase where we kind of want us to sort of replicate that line of work from NLP. We're very much inspired and looking up to them. But we don't have exactly, first of all, we don't have a big data set. Our biggest data set is something like ImageNet. And I'm talking about public data set here.
Mhm.
Something like ImageNet, which is 1 million images. And Imagen has been a fantastic data set. It served the community for 10 years. But the problem with ImageNet is that, first of all, it's been around for not quite a while. It's a frozen data set, so nothing changes. So as we develop new ideas on a data set that is constant and kind of frozen in time, we tend to sometimes our ideas overfitting on that data set, and
Mhm.
these a lot of the gains that we see in images don't actually transfer, and that makes sense. We've been dealing with this data set for a while now. um, I would actually say that maybe we've trained more models on pixels on ImageNet, but I'm not going to get there. And then the other question, of course, is what are our downstream tasks that we're showing that performance in? And this is another sort of sore point for us computer vision people, where we're also seeing a little bit of a kind of sad state where we have our object detection and maybe our segmentation, but they're all essentially classification tasks. We don't have the richness in output and in tasks that NLP has. All of our pre-training is classification, our downstream tasks are classification. So it's really hard to tell if we're actually making progress or not. So this is something
Mhm.
I think that it is for the community to think about.
I guess a couple of reactions to that. One is maybe the second one informs the first, but there's classification, but then is the idea that all of the complex problems that we think of, like bounding boxes and all these other things, they kind of just boil down to classification. So at the end of the day, it's all classification, even if it looks more complex.
Correct. So there isn't. That's absolutely true. And I mean, our most complex task, I would say, maybe is object detection, because it involves sort of maybe predicting intermediate boxes, and then on top of that, you want to classify the object type, or maybe predict other 2D properties, like by classifying the pixels within those boxes.
Mhm.
But even that is cast as a classification.
And what about things like VQA, visual question answering? Is that more? Do you think of that more of an NLP task than a vision task, or?
The only thing I have to say there is that, and this was also a point made by, Clip, a great paper that came out last year, is that even there, the data sets are very small, and we really can't tell how effective these methods are because we really don't have a good sense of these tasks. Um, and I mentioned Clip, which is a prime example that showed that all the gains for transformers came when they downloaded that huge data set of theirs. Like, I think it was 250 million image text pairs. We don't exactly know the source where the data set is from, but we know it's from the web. And this is how, and they were only able to show that amazing property of capturing jointly images and text when training on such a huge data set. Um, so this is sort of the what we aspire to get to, having training on such large images. And of course, that comes with a lot of other questions about, are we doing our due diligence and making sure that this is a good, you know, data set in terms of ethics, in terms of like content, like are we making sure that it's an unbiased data set and so forth, which brings, of course, new challenges. But I feel that for we need to move to that scale, or otherwise we're going to kind of be stuck in our little ImageNet sort of standard regime, which is not a good state to be in.
Yeah, yeah. I think the data set side of that was my second question, and that was we hear about and see new image data. On the one hand, we hear about and see new image data sets, all the time. They tend to be specialized and fairly small. On the other side, just like NLP had access to the web, Vision has access to the web. There are tons of vision, or there are tons of images on the web. Do you think that in order to get beyond kind of ImageNet and classification, we need to define like unsupervised problems or semi-supervised problems beyond just kind of simple label, supervised learning types of problems? Is that the big, one of the big barriers?
Yeah, I think that's definitely one big barrier. The problem with vision, and actually with all data sets, is that collecting a large scale data set by crawling the web and just releasing it is almost impossible. And maybe for a good reason, as in, you have to make sure that you have consent from the creators of the images to actually release them. Um, you also want to make sure that we are now entering the stage with in AI where it's no longer opportunistic. We need to be very cognizant of the data that we're using, the models we're putting out there, how they can have, like, maybe they can have potential harm. And so these are all aspects of our work, and we're responsible for it. It's not like someone else is responsible. So there is actually releasing and collecting and releasing a large data set is a huge responsibility that comes in a lot of work, and that might be a roadblock to seeing larger data sets coming out. I don't have a solution to that problem, but I feel that if there is motivation to go there, I think we'll make that happen. And I think that we also need, and this is maybe my own personal opinion, we need to rethink the problem that we're solving, these pretext tasks that are commonly referred to as sort of the task that you try to solve either in self-supervised learning. For example, in BERT, it was filling in the, like, masking words and filling them in. We've seen recently work from actually my lab and Kaiming and colleagues, where they do the same thing, but they mask out patches of the image and they try to fill them in. These are all this is a great task, but it is still sort of constrained to be on just in predicting pixels. We need to enrich in our these pretext tasks if we want to maybe solve for richer tasks, downstream tasks, moving beyond classification. I don't think that having a simple pretext task will solve complicated tasks down the line, like maybe 3D reasoning or 3D understanding, which is a field that I've been working on. I do think that there's limitation in transferring that, so we need to account for that. And so but I think it's a good first step. I think that we just need to broaden our horizons a little bit on what problems we're solving, how we're solving them, and how we're thinking about building representations, either through self-supervised learning or through supervised learning with labels, but move out of this image to single object label, let's say.